Hi there, good afternoon, and welcome to our Strategic Partner webinar on Additive Manufacturing Cybersecurity with Oak Ridge National Labs. My name is Lynn Dome, Women in Cybersecurity Executive Director. We often go by our acronym WeSIS, as in We Sisters, and that's exactly what we are. We're a cyber sisterhood. So I'm going to go ahead and share my screen and just give you a little bit of information about the WeSIS organization. Hold on just a second here. We'll play it from the start. So our mission is to recruit, retain, and advance women in cybersecurity. We have over 4,600 members, comprised of women, male allies, and advocates, all with a strong mission and passion to engage women in their cybersecurity careers. And we do so by creating opportunities. So we have many different initiatives. We have our webinar series, like the one you're joining here today. We have our virtual and in-person career fair. Our spring virtual career fair is actually March 25th, so it's coming up shortly. We have an online member forum, and within our member forum, we also have special interest groups like neurodiversity in cybersecurity, Latinas in cybersecurity, data privacy, cybersecurity law. We have many different training programs like the SANS Security Training Scholarship made possible by Google, the AWS Learning Series, and the Gamified Cybersecurity Challenges made possible by Target. We have newsletters, our annual conference, which is September 8th through the 10th, and scholarship grants and awards. So good thing to note is that Monday is the deadline to apply for scholarships, grants, and awards. We have student scholarships, faculty lodging grants, BIPOC fellowship awards, and veteran fellowship awards. And also Monday, March 1st, is the deadline to apply for the call, or to submit to the call for presentations as well. You could find all that information on our website, wesis.org, under the 2021 conference. We have many different speaking and media opportunities, our Job Board Plus, where all our members can upload their resumes and update their profiles, and our strategic partners recruit from year-round. We participate in market research or virtual summits. We have a very strong Veterans Assistance Program that includes our Veterans Apprenticeship Program. Applications for that will be opening up in mid-March. A speakers directory, a mentors-mentee community, which is really fun. We have 707 mentees, 185 mentors in this 12-month structured framework that's developed to upskill and up-level women in their careers to prepare them for their next level of advancement in their cybersecurity careers. Allies and advocates for action, and then also 34 professional affiliates and 114 student chapters, and many, many, many more initiatives in the pipeline. And we all owe that to a special thanks to our WeSIS founding partners, Cisco, Facebook, and Palo Alto, and our strategic partners, AWS, Bloomberg, Cisco, Facebook, Federal Reserve Bank of New York, Flatiron, Fortinet, Google, Here Technologies, IBM, Lockheed Martin, Microsoft, Nike, Oak Ridge National Lab, who brings you this webinar here today, Optum, Palo Alto Networks, SANS Institute, SAP, SentinelOne, SpearTip, Starbucks, Target, University of California, San Diego, Verizon, and Workday. So just a little bit of housekeeping is that everyone will receive a recording copy of this session when it's all done rendering. Also, this is to be as interactive as possible. So we have the wonderful Tiffany here to present today, and she'll also be available to answer your questions. So please, at the bottom of your screen, there's a section there for you to put your questions in there, and she'll be getting to those at the end of her presentation. And so before I hand it over to Tiffany, I'd like to encourage everyone to grow with us, be a part of the WeSIS community, subscribe to our newsletter. We have a Facebook page, a Facebook group, a Twitter, we're on Instagram, you're on LinkedIn, so you could find us everywhere and engage with us. You could subscribe to our newsletter, and you could also join our community. And all that information is, again, available on our website, wesis.org. And so with that, I'll go ahead and stop sharing my screen, and I'd like to hand it over to Tiffany to take it from here.
All right, thank you so much for the introduction, Lynn. Like Lynn said, my name is Tiffany Potok, and I'm from the Oak Ridge National Lab. I really appreciate everyone being here today. I know virtual presentations can be a little weird. For me personally, I usually bring candy to bribe my audience, and I found out in my last virtual presentation, it doesn't have quite the same effect bouncing off the screen back at me. So I'm gonna go ahead and share my slides. All right, let's see. Can everyone see that? Go with yes. All right, so Today I'm going to be talking about additive manufacturing cybersecurity and how different perspectives are essential to creating a successful cybersecurity village. So before I get into that, I want to talk a little bit about my own background and my journey to getting to where I am today. I was exposed to cybersecurity and computer science from a young age because my dad is a cybersecurity or a computer science researcher, and he's actually here today. Hi, Dad. And he would always come home and tell us about the really amazing things he was able to do with computers and computer science, and that was really inspirational to me. So naturally, when I decided to go to college and was choosing a major, I decided on psychology. I did this starting at the University of Carson-Newman and through a study abroad at the University of Glasgow, Scotland, and finally graduating from the University of Tennessee, Knoxville. All of these different schools gave me different perspectives on psychology, from psychoanalytic to cognitive behavioral to neuroscience, which actually furthered kind of my interest in my next degree, which is computer science, because a lot of the psychology models we were looking at actually involved computer science, which really sparked my interest. And I've always had a passion for national security. And so when I heard about the National Science Foundation Scholarship for Service Cybercore program at the University of Tulsa, I jumped at the chance to participate. And that's how I got my Master's of Science in Computer Science with an emphasis in cyber operations. While I was at the University of Tulsa, I was able to participate in an internship with the Oak Ridge National Lab, which led to my position as a cybersecurity technical professional. And actually, all of the work that I am presenting on additive manufacturing comes from that internship. So I'd like to talk a little bit about the amazing, incredible team who did all of this work and that I got to be a part of. I really want to thank this team because we were supposed to have a summer internship this year, 2020, and like a lot of things in 2020, that didn't quite end up looking how it was supposed to. And with additive manufacturing being a cyber physical system, we were really looking forward to being able to be hands-on with these machines and getting to learn about them from both the cyber side and the physical side. But with our internship going virtual, that was a little bit of a challenge. And this team was incredible at making that challenging experience really rewarding. And I think the work that we've done will speak for that. So I want to talk about each of these team members, starting with the University of Tulsa. Alex Van Stockham, she has a background in history and education and spent a little bit of time as a teacher before she pursued her master's degree at the University of Tulsa in computer science, where she is currently working on her PhD. Like Alex, Beth has her master's and is working on her PhD at the University of Tulsa, and her background is in mathematics. Carson Ellsworth is getting an undergraduate degree in computer science from the University of Tulsa as well. You guys already know about me, and after graduation, I defected to the ORNL team. So the ORNL team also has a really wide array of backgrounds. So we've got Curtis Taylor, who is a computer science background through and through from bachelor's to PhD. Joel Dawson, who has a communications degree as his bachelor's with an emphasis in film and media arts. And then Rob Jordan, who also has a computer science background. I think that this team having such a wide, multifaceted perspective is really what helped us through this virtual learning experience with additive manufacturing. And that really was interesting and sparked my interest in all the different perspectives that are involved in cybersecurity. So let's look at what the community as a whole looks like. So obviously, since we're talking about cybersecurity, computer sciences and information sciences are incredibly important because you have to have a really good foundation in computer science if you're going to try to understand this cyberspace and this cyber perspective. So that 40% really makes sense. Likewise, this 30% in business also makes sense if you think about all the things that you do in the cyberspace related to business with online shopping, online banking, investing, and so many other areas. It makes sense that this business would be the next most significant background for this cybersecurity. But who are we missing and why does that matter? So I want to talk a little bit about this little group over here, the underrepresented side. So my advisor from the University of Tulsa used to say, or I think he probably still does say, I can teach you computer science, but I can't teach you what you already know. And I think that he realizes that as the cyber world extends into these physical worlds and these other domains, that in order to have true cybersecurity, truly secure cyberspaces, we have to be able to understand and look at things from different perspectives. And personally, I can say that having my psychology background, I think, has given me a different view on cybersecurity than people who have a purely cyber background. And with engineering and engineering technologies specifically, it's really important, especially with cyber physical systems and manufacturing and looking at power grids and things like of that nature, to look at and understand that engineering perspective. For example, take a look at what happened in Texas last week. The Texas power grid was crippled by these winter storms, and it was really devastating to a lot of people, and people were without power for days. And that is just with a natural disaster. Imagine if that was a cyber attack. This space has enormous risks from the cyber perspective. And while the cyber perspective of protecting this space is really important, it's almost more important to have people who understand these spaces and these power grids and these areas, who can tell you where the vulnerabilities are and who can tell you the important parts that need to be protected in this cyberspace. Obviously, I'm a little biased with psychology and social sciences, but if we're talking about cybersecurity, a big vulnerability in cybersecurity is the human element. And people with a psychology and social sciences background understand that human element in a different way than traditional cybersecurity professionals. And being able to see things from the user's perspective or the attacker's perspective, or from a social engineering attack, is really important in cybersecurity. Looking at English, communications, and the arts and education, all of these areas really are strong in presenting information and in a coherent way and making sure that other people can understand that. And so looking at education, I mean, think about how much education has changed in the past year with the pandemic, and how everything with education has really shifted over to this cyberspace. Protecting that has been a challenge we've seen throughout this pandemic. And looking at visual and performing arts, especially in the media, one of the huge threats and challenges that is facing our nation as far as propaganda is this idea of these deep fakes, or these videos that can be created to look like realistic and valid videos that are fake and have been created by using specific math algorithms and using really complicated techniques, that if you have that understanding of how these videos are supposed to look, that's very valuable in trying to detect and prevent that. And that feels like a good segue to talk about mathematics. Looking at those deep fakes and understanding how those algorithms work can help debunk those videos and be able to tell the real from the fake. Additionally, math is really important in looking at all of this immense amount of data we have and trying to make sense of this data and understand what data means and understand if it's a cyber attack or if it's regular behavior, and being able to differentiate between those spaces. Biology is also an area that's becoming much more technical, as if you look at the hospitals and how those have become much more based and reliant on cyber technology, along with modeling for viruses and things like that, that are done in a cyberspace but really need a biology perspective to be understood. So with that, let's shift over to another area that has a need for a village as well, a village of different perspectives, and that's additive manufacturing. So when you marry additive manufacturing and cybersecurity, you really do need a full village of a lot of different people in order to really have this become a secure space. So today, with additive manufacturing, I'm going to be giving a high-level overview of what additive manufacturing is, segueing into additive manufacturing and national security, talking about a few of our successful vulnerability exploitations that this team that I'm a part of has pulled off, and then finally ending with what comes next. All right, so what is additive manufacturing? Additive manufacturing is building 3D objects by adding layer upon layer of material. Those materials can range from plastic to metal to maybe even one day human tissue. But before that building begins, you have to start with this 3D model. The model is then sliced into layers using a special software called a slicer. These slices represent the layer of the model that will be built by the printer. And then these are sent as G-code to the AM device. And if everything goes well, you have a 3D object at the end. So let's go into a little bit more detail on all of those areas, starting with the computer-aided design. So this is usually going to come in the form of an STL file, which is just a file ending. And there are other versions as well, but this is the most common. And so this model can be created either using your own technology and you creating something for yourself, or you can download something from one of these print databases that are online and have hundreds, if not thousands, of different prints that you can pull from online and just plug into your slicer. And next thing you know, you have that object, such as Baby Yoda, which I actually do have a Baby Yoda myself, and that came from one of those print databases. And while that's a really cool idea, there also does not seem to be a lot of checks and balances with the security on that. And to me, it seems like it could be a potential vulnerability if they're not checking to see that the file that's uploaded is what it's supposed to be. But anyways, let's move on to slicing. So slicing translates a computer model in the G-code, which is known as the geographic code, which essentially just gives the printer instructions on how to move, where to move, how fast to move, and how much material to extrude while it's on its trajectory. And that sounds really complicated, so I figured an example would help. This is an example line of G-code that would probably just be a small part of a layer. It definitely is not the entire layer itself. But it starts with this G-code instruction, which is essentially telling the printer head, which you can see in the animation up top, to move in a straight line to these coordinates at this speed and extrude this much material. And there are all kinds of different G-codes that can tell the printer to do different things, from change the units to move in a circle to go back to the origin. And it's a really powerful tool that a lot of times is sent from the printer to the AM device in plain text, which is surprisingly easy to read and can be captured and manipulated. All right, so moving on, let's talk about the additive manufacturing device and the printed object. Additive manufacturing is an incredibly broad spectrum. There are lots of different types of machines, lots of different machines within those types, and it's very difficult to kind of categorize additive manufacturing in a simple way. So our team decided to look at additive manufacturing from the state of the material before it is printed. So the input side of this additive manufacturing device. So let's start with powder. Essentially, powder means that you're going to have a powder of some kind of material. It's usually metal, ceramic, or plastic that is input into the machine. And then in the example you see here in the animation, which is direct energy deposition, that powder is actually fed into this nozzle that has a laser or some kind of other heat source, usually a laser and an electron beam, that will melt that powder and create a melt pool, which is then deposited onto the build surface, as you can see in the animation, which is actually showing the transformational challenge reactor core, which was created at ORNL using additive manufacturing. And as you can see from this demonstration, it is creating an incredibly unique part that's much faster than traditional manufacturing methods and has a lot less waste. Because if you think about traditional manufacturing, it's usually from a subtractive perspective. And if you're looking at things from a subtractive perspective, it's difficult to sometimes get those intricate parts. And then at the end, you do have a lot of waste because you have to shape this block into the part that you're looking for. However, this isn't the most efficient type of manufacturing from a cost perspective, as the printer itself is incredibly expensive and can be a little bit sensitive and require maintenance. And a lot of these parts, once they're done being printed, do require some complex post-processing to get a smooth finish or to really secure the product. All right, so moving on to liquid. So some of the materials used in liquid 3D printing or additive manufacturing are UV curable photopolymer resins, plastics, other resins, and other polymers. In the example that you can see in this animation below, this is actually what's known as vat photopolymerization. And essentially you have this large vat of liquid that the part is dipped into, as you can see in this diagram, and then a laser or some kind of UV light source is used to cure a layer of that liquid resin onto the part. And then it's swept back, as you can see in this animation. Liquid additive manufacturing is highly accurate, low waste, and has a really nice, clean finish. However, it is still relatively expensive, and there are limited materials that can be used. And a lot of times there is post-processing required to really strengthen or re-cure the part so that it is as strong as it needs to be. Finally, let's talk about solid, which is probably what everybody thinks about when they hear additive manufacturing. This is something called, or the example that I'm talking about is called fused deposition modeling. And this you can use a wide array of different materials. Some of the more common ones are thermoplastics, plastics, polymers, and resins. And so those essentially are used in the form of what's called a filament, which essentially, if you think of a spool of thread, it's something similar to that, except it's one of these materials. And then that is fed kind of like if you were using a sewing machine into this hot end extruder and then layered onto the build platform, as you can see in this probably very familiar animation. Some of the advantages are the printers themselves are very inexpensive compared to the other methods, and the materials themselves are also fairly inexpensive. It's also the most common form of additive manufacturing, so there's a lot of different parts that are available online, and there's a lot of different experience out there. There's also customizable open source firmware, so you can really use this printer and make it your own and customize it however you want it to be. Some disadvantages are the finish is not always very good, and that can be determined by the extruder nozzle size, because if you have a larger extruder nozzle, that can mean that you have more visible layers. But if you have a smaller one, that also means it's going to take more time to do your prints. So while this is a really cool technology, there are still some downsides. But anyways, let's talk about some of the reasons that additive manufacturing is really great. So it's great for rapid prototyping, complex geometrical shapes, and low volume manufacturing. For example, if you look in the lower corner, you can see the final version of the finished version of the transformational challenge reactor core that we saw printed in the powder slide, which is really incredible because it's one of those things that you're not going to need a tremendous amount of, but it is incredibly complex, and seeing something like this be created using additive manufacturing, it's created much faster than if this was created in traditional manufacturing methods, and it's really cool to see. It's also repeatable, and once you have that model, you can use it and you can print it yourself as many times as you want using the same printer, or you can send it to someone else and then they can print that exact same standard model. Or if they wanted to make it a little bigger, for example, if you wanted a 2-foot baby Yoda and you had a printer that would allow you to do that, you could scale up the design that I used, or that was used to create my baby Yoda, and scale it up to that, or scale it down to 2 inches. And what I was talking about with the nozzles, you can kind of see a little bit in this picture how Baby Yoda has slightly more visible layers, whereas my Mandalorian helmet has a much smoother looking finish. But both parts are still pretty incredible and proudly on display in my home. All right, so let's talk about some things that have been done at ORNL. So one of the cool things is this 3D printed excavator. It was printed in, I think the metal arm took about 5 days to print, but the cab itself only took 5 hours, and they were printed on different types of printers, but it's really cool to see something like that come together so quickly. There's also this submarine that is the Navy's largest 3D printed asset, and it was based on a SEAL deployment vehicle that usually takes about 3 to 5 months to produce, and it was produced at ORNL in 3 to 4 weeks, and the cost was reduced by 90%. This wind turbine blade mold was also printed at ORNL, and successfully there were several wind turbine blades that were printed off that. And probably the most interesting thing on this slide is the 3D printed Shelby Cobra, which was printed at ORNL. And from the idea in someone's head to say, hey, I wonder if we could 3D print a car, to the time that this car was ready was about 6 weeks. And all of these are really cool examples of additive manufacturing, but also represent different areas where there's opportunity for different perspectives to be involved. For example, construction, using this excavator, creating this excavator, looking at the engineering perspective, looking at the military perspective on this submarine, looking at all of these different perspectives from energy to automotive. There's clearly evidence that this wasn't just something that was done by additive manufacturing. This is something that was done by people who knew the materials, who knew these different sectors, and all worked together to create really cool products. For example, here's another one. This is the Additive Manufacturing Integrated Energy Demonstration. Essentially, back in 2015, ORNL partnered with several different industry partners to work on this idea of creating an energy efficient system in an energy efficient way. So creating this system was incredibly energy efficient. And then the system itself is also incredibly energy efficient. The house itself was completely 3D printed and has solar panels on the roof that can power not only the house, but if the car needs power and there's excess power from the house, that can flow into the car. But if it's not a sunny day, then the car can actually power the house. And the car is also designed and printed with additive manufacturing. And this symbiotic relationship, again, just shows what is really possible when you have people who have different expertise and different perspectives coming together to work on these projects. Because this project isn't just an additive manufacturing or a cyber project. There's electrical engineering, architecture, home design. There's so many different elements that go into these projects. And it's really amazing to see all of that come together and what's capable when people from different backgrounds and different perspectives come together. So just on a more general note, some of the critical infrastructures we talked about in the last couple slides: commercial manufacturing, energy with the nuclear and the wind, and defense with the submersible and several other elements, and transportation with the cars, and also aerospace is using additive manufacturing for critical safety parts. All these industries are affected by additive manufacturing, especially healthcare. If you think about it, in this global pandemic, we've seen additive manufacturing used for personal protective equipment, ventilator masks, testing swabs, and so many other areas outside of the pandemic. But it's really been cool to see additive manufacturing utilized in this way. The chemical is also really interesting from the perspective of creating stronger materials, or maybe eventually printing pharmaceuticals or biological materials. And this idea of these critical industries being important in the future is so acknowledged that the Department of Homeland Security actually published a report earlier last year that examined how these different industries are incorporating the different types of additive manufacturing and how it could impact national security. We can see from the figure the projected timeline for advancements in additive manufacturing in different areas, including 3D printed safety critical parts. For example, Navair flew an aircraft containing 3D printed parts in 2016, and those were safety critical. Of course, with all these new advancements does come new risk. So these are some of those areas. Sabotage of safety critical parts is one of, if not the most significant concern in this area. If a malicious actor can damage a part with no obvious evidence of change and cause it to fail critically, that attack would not only be potentially devastating, but it would also be incredibly difficult to discover and could cause a tremendous amount of damage. Take, for example, the picture in the background of this slide. We already know that additive manufacturing is involved in the production of wind turbine blades. And when they fail, they tend to fail fairly critically. And intellectual property theft, this is another high-risk area for additive manufacturing. And a new risk with this IP theft is associated with the idea of reverse engineering. So, for example, in 2017, scientists at Siemens were able to reverse engineer a part from a nuclear plant in Slovenia. And now this part was broken, and the company who originally created it had gone out of business. So this was really the only way to get a new part, and it was really a beneficial case of reverse engineering. However, it is also interesting to look at from the perspective of a malicious actor. For example, if we're talking about weapons of mass destruction, or something along those lines, or those kinds of reverse engineering, or reverse engineering in this area could lead to the weapons of mass destruction being able to be created by malicious actors without the need for specialized tools or experts. And this is much simpler with being able to just take a part and examine it and use different technologies to be able to model it and then print it. And with additive manufacturing and rapid prototyping, that's a lot easier than it used to be. Additive manufacturing also doesn't have a significant tracing or a purchase trail for the parts that are created, which leads to this possibility for untraceable weapons. And this isn't just a possibility. Blueprints for handguns and assault rifles have been floating around the internet since 2013, and many of these blueprints have actually been printed and successfully fired in tests. In fact, the synagogue shooting in Germany in October of 2019 used improvised guns that included 3D components, or additive manufactured printed components. And as more sophisticated printers and materials become more readily available, this threat is only growing. Additive manufacturing hardware and the accompanying software supply chain is also somewhat vulnerable because a lot of these material and software are manufactured outside of the US, which leaves it vulnerable to sabotage or spyware. As we are still dealing with the fallout from the SolarWinds fiasco, there's no telling how dangerous a breach in this area could be, especially if for printers responsible for safety critical parts or software going into sensitive locations. So now that we've talked about all these risks, let's look at this drowned cyber-physical attack with additive manufacturing done by Sofia Belovsky and Mark Yampolsky, as well as several others. This drowned paper explores a sabotage attack on a replacement propeller for a quadcopter unmanned aerial vehicle, or as most people say, a drone. And essentially what the authors did is they took a print design file, like one of those STL files or CAD files that we looked at earlier, and they made modifications to the file, not the code or the communications, but to the file, and then printed those parts to see if those parts could be determined to have faults or if they would look like every other part. And they looked like every other part. However, as you can see from this photo, they failed catastrophically. The idea behind this attack would be that you would gain remote access, probably through a reverse TCP shell using a phishing attack. And then if the victim computer had these parts, you would replace the unmodified designs with the modified designs, which is really great for the proof of concept that parts can be modified and then have no evidence of being modified, but still fail catastrophically. And if you think about it, this is a low priority target, but the same kind of idea could be used on critical infrastructure. After all, a rotor blade is not all that different from a wind turbine blade in regard to weak points. All right, so now that we've talked about these threats, let's talk about how our team tried to visualize this in a threat landscape. So this threat landscape, the idea was if we could have a landscape that was generalized enough to account for any AM device, but specific enough to include all possible variations of AM hardware and software, which is a pretty big ask because that's a wide array of machines and materials and softwares and hardwares that all have different purposes, and really it is quite a wide array. So we looked at some of the existing threat models, and we looked especially at this MITRE ATT&CK ICS framework, which I'm only showing you half of because of the incredible detail that this attack framework has. And that was something that was really inspirational to us, because you could click on any of these boxes and be pulled away to a description of this attack. And it was incredible for the control device and device-to-device communications element of this additive manufacturing process. However, it didn't really have the visualization that we were looking for. And that was something that we saw in this Purdue model, which had these really nice layers. And so that was kind of what inspired our thinking with this threat model. So I know this is impossible to read, so I'm not going to go through this in too much detail, but essentially our goal was to have this top layer be the most basic description possible. So you have power, general device, device-to-device communications, AM device, and post-processing. And then with each layer, we get more specific about the parts, listing out hardware, software, and then specific hardware and software. And on the third tier, we get to those three different types we were talking about earlier: powder, liquid, and solid-based AM and those different parts that are involved in those processes. So we wanted to see if this would actually be applicable in the wild and be an effective way to display an attack. So we used an attack that we had successfully orchestrated with a man-in-the-middle attack, and we tried to trace that through and see what areas of our threat model would be affected, and if there were areas that would not be affected or might not be as significant. And then we found that this worked pretty well, but we wanted to also look at some of these other models that we had looked at previously and kind of compare and contrast and see if there were gaps or things that were missing in our model or in their models. And we found that this left-hand side was really great and showed the control device and the device-to-device communications really well and kind of covered that area, but left this right-hand side, which was more of our physical space, a little bit blank and kind of unaccounted for. So we came up with some specifics like file manipulation, memory modification, and a few other things to kind of cover that area and see where just a few areas were missing in this additive manufacturing version of our threat model, and see where some of these holes might be in some of these other threat models. We know the attacks that exist, and we've done them ourselves, as you'll see here in a minute, but there just simply isn't a good framework to represent this developing environment. And ours is a living document, and there's a lot still that we're working on with it, but we're really trying to incorporate both the cyber side and the physical side and make sure that we represent the attacks on the cyber side as well as the cyber physical side. So let's talk about the attacks. Our first one is what's called a man-in-the-middle, as most of you probably know. And essentially, this was on a $15,000 proprietary printer or a commercial printer. And our attack happens right before or after a connection is established between this printer and the additive manufacturing device, which is done through an auto discovery feature on the control device's software. So let's look at what a healthy version of this would look like. So a healthy version, you'd take your STL file, throw it through the slicer, and then that sliced file would be sent to the printer control software. And once the software receives that, it would send out a broadcast message going, hey, are there any printers available? And then the printer would respond and say, yep, here I am, I'm a printer, I can help you. And send its name, serial number, and IP address to tell the control software who it is. Unfortunately, there is no authentication in that step, which is where we came in. Here we go. And while listening on a separate device, we were able to see this exchange happen. And then after the printer responded and said, yep, I'm here, here's my information, we were able to come in as the man in the middle and send a message to the printer mimicking that message, or send a message to the control software from the printer, mimicking that message with everything the same except sending our IP address instead of the printer's IP address. So now everything that the control software sends to the printer, it thinks it's sending to the printer's IP address, but it is really sending it to our man-in-the-middle IP address. And then we can choose how that gets back to the printer, which is incredibly stealthy, and we have complete access to all the files being sent, and we could do any number of part sabotage. Like, for example, the drowned attack. We could insert our files here and print those modified files, and there we have it. The next attack we looked at was regarding capturing a password. So we knew on this commercial printer that it had this special commercial software running, and that was, you had to have a password in order to view, change, delete, or modify any of the prints in the printer queue or in the print history, which is good if you have multiple users on the same account trying to print, so you can have your print queue in the right order and make sure that everybody's having equal access to the printer. However, when you set that password, which we did on one device we were not the man in the middle at this point, to be fair. On the first device, we changed the password, as you can see, which was sent in plain text, which was Win7. And this was captured on a separate device that was just on the network listening. And we were able to capture this packet and see the password in complete plain text, which is really cool and maybe not the most secure. However, if that seems like a lot of work, you could always just go to their other commercial software and delete things from the queue without needing a password. So, you know, the security there is maybe not the best. Our final attack kind of came with the goal of part sabotage. Our goal was to find a way to compromise the structural integrity of a print with leaving no trace, and to do this without having to, or just by looking at memory modification. So for this attack, we chose this small bomb toy because bombs are built to specific dimensions in order to function properly. And if it's not done just so, it's not going to work the way you want it to. So we decided to attempt to compromise the top part of this print, as it comes in 3 parts: this top, the middle, and this bottom part, the fins. And we thought because that would be the point of impact. And so if we could find a way to compromise that top part, then that would be the part that would be critical for compromising. All right, so this is happening after the model has been sliced, and that slicer is storing, or that sliced version of the model is being stored in memory. That's where we're modifying it. So it doesn't change the files, and the user would have no idea that this is happening. So just as kind of a refresher, slicing software is the software that converts the STL models into G-code. And in the software that we were looking at, that G-code was stored in plain text, which is incredibly easy to read and manipulate if you know the structure of it, which we all definitely are experts on now. And so here we can see what that G-code extraction looks like. This modification process worked by extracting this G-code as it is read in by the processor memory and then modifying it to erase the infill, or the structural support center of the print. If we think of the print like a wall, the infill would essentially be the insulation layer between the 2 layers of sheetrock, which we were seeing if we could just do a brute force kind of removal of that, if we could compromise this part. So the modification results, we were able to remove this infill, or the skin, which was done with some visible differences, but none that would obviously show that the integrity of the part had been impacted. Both of the tops weighed 31 grams and the body weighed 118 grams. And so to see if they had been compromised, we decided to drop them, and I say we, it was Curtis Taylor. He dropped the 2 print heads with the body from 60 inches, and we got proof of loss of structural integrity. As you can see from the modified inside, there's a pretty substantial crack on both the inside and outside in comparison to this non-modified outside. This is a first pass at this attack. And if we had experts in materials or nuclear or the structural components of these parts, this attack could have been much more specific. It could have been much more damaging. You can see the damage up close. This was pretty significant, and this was just looking at it from the cyber perspective. If we included other perspectives, this could be much more refined. Additionally, including these other perspectives would encourage and help us secure these really critical infrastructure pieces and make sure that nothing is being compromised. Because looking at things from the cyber perspective, you can't always tell that there's been an attack. But if you have experts who know the materials and the structure and what's supposed to be in this device and what everything is supposed to look like, then they can help secure it and see if things go wrong. So, in conclusion, our next steps are going to be creating this additive, or enhancing our AM threat model and coming up with a little bit more of a detailed version based on these different printer types, coming up with a cybersecurity playbook that offers detailed cybersecurity threat analysis based on some of the exploits that we've done for additive manufacturing. We're also looking into firmware and doing some in-depth analysis of the open source materials available. All right, so I know I've thrown a lot of information out at you guys. But just to summarize, we've talked about how you need a village for cybersecurity to be really effective. We've talked in probably a high-level overview of additive manufacturing. We've looked at how to create a threat model for additive manufacturing, and that's a living document that is continuing to be worked on, and how that could potentially help mitigate some of these threats. And we've talked about some of the threats, the successful vulnerability exploits that we've been able to accomplish. And so I have my citations. And before I go any further, I really want to give a special thanks to the ORTU team sponsors, Leo, whose background is in chasing mice and catnip, and Sally, who really excels at tail chasing and stick eating. They were incredible helps to us in this project. So I'll look over here to the questions. Oh, it appears I don't have any questions yet, so if you have any questions, feel free to ask. So Lynn, if we don't have any questions, do we want to go ahead and move on?
Yes, sorry. Yeah. So, so thank you everyone for joining us today. You could certainly sync up with Tiffany on LinkedIn, connect with her, ask her any additional questions that you might have. And if you have anything, always reach out to WeSys at info@wesys.org or to myself at lynn@wesys.org. And so that's a wrap. Tiffany, it was a wonderful presentation. I really appreciate your time and attention and your commitment to putting this incredible presentation. We had a tremendous amount of viewers, so it was fabulous. And so until next time, we'll see you all and have a wonderful, beautiful, safe rest of your week.
Thank you, everyone.
Thank you. Bye-bye.